use this as a basis for discussion because it has a lot to teach you also about the physics of spin chains and other things. So let's just mention a few differences between the repulsive and the attractive case, because there are quite important differences. So what we do is that, just for the notations, I'll denote minus C as C bar, so C bar is a positive number. And now the beta equations that we have, if we write them, they look like this. So yeah, let me use exactly the same notations as in the notes. So we now have a product over beta different of alpha of lambda alpha minus lambda beta minus I C bar over lambda alpha minus lambda beta plus I C bar. Okay, so just thinking a little bit about this, you can see that the situation is completely different to the repulsive case, because if you, for example, consider a lambda that has an imaginary piece. So say, for example, that the lambda alpha here has a positive imaginary piece. Then, of course, the left-hand side, in the limit L going to infinity, will collapse to 0. Okay? Right? So that means essentially, if you look at the right-hand side, there has to be. So you won't get anything out of the denominator for for finite lambdas, but you could get a 0 provided there was a lambda beta, which was such that it was equal to lambda alpha minus IC bar. Okay, so if you have a rapidity with an imaginary part, say here, then the only way you can fulfill your equations in the limit when L goes to infinity is if there is another rapidity sitting C bar below in the imaginary direction. Okay? Conversely, if the imaginary part of lambda alpha is negative, okay, then the left-hand side blows up to infinity, and then you need to have a cancelling in the denominator. That means that there should be a lambda beta such that the imaginary part is C bar above that one. Okay? So if you've got an imaginary part here, then it wants to have, partner is going down. And then if it's under the real axis, it wants to have partners going up. Okay? Now there's something which I can't prove to you, but the solutions to beta equations are self-conjugate. Okay? So if the first statement is that if you have a set of lambdas that are solution to the beta equations, then the set of the conjugate solutions is also solution to the beta equations, automatically. However, a more insightful statement is that every set of solution to beta equations is self-conjugate. The set is the same as the conjugate set. Okay? So the patterns that you can get for these complex rapidities essentially is what we call strings. So what we can have as solutions are these strings. Strings are now admissible. And the way a string looks is if you have the complex plane of lambda. Okay, so that's a one string. That's a two string. And then the distance between these two is I C bar. And you can have, for example, I don't know, a five string. Well, it's kind of uniformly spaced, as you can see. And the distance between every element here is I C bar. Okay, these are now admissible solutions to the beta equations. If you think about your wave function, the physical interpretation of these solutions is quite clear, because now the rapidities take an imaginary part, you substitute back into the form of the beta wave function that we saw at the very beginning, and what you see is that there's, once you normalize your wave function and you do it properly, what you see is that the wave function has exponential decay in the relative coordinates of the particles within a string. So a two string would have one relative coordinate such that the the wave function is exponentially decaying as a function of increasing distance between these two particles. So instead of being, so in the repulsive case, if you imagine your Hilbert space as Rn, then your wave function is essentially extended in all of Rn. Okay? If you take any patch within Rn like that and calculate a portion of the amplitude of the wave function in there, you'll get a finite number. But in the attractive case, what happens is that this extent of the wave function in Rn gets sliced, okay, by a number of dimensions, which is essentially the length of the string minus 1. So if you have 1,2 string, then the wave function of a 1,2 string in Rn has one of the coordinates such that the wave function is exponentially small for all values of this coordinates except at one point, and then it goes to 0 again, exponentially. Okay? If you have a 7 string, then you lose 6 directions. Okay? So these are just bound states of particles in there. So that's quite interesting because, of course, it changes the physics radically. Okay? Let me just introduce some notation. I don't want to spend hours on this because it's it's a bit technically involved, and you can read about it in the literature. But I want to say some things because maybe, Martin, did you do strings yet?
Not yet.
Okay, so you will meet strings in spin chains. So in spin chains, strings are inevitable. They are always present. You will always have to open up the space of excitations to string states. Whereas in the Bose gas, they are only there for the attractive case. So the form of rapidities within a string is like this. So one notation which we've used in the past is like this. Okay? Let me just write it down and tell you what this is. Actually, let me even be more finicky. And here A equal to 1 up to J. So this is for a J string. A length J string. A length J string is characterized by a center, that is the coordinates on the real axis representing the center of mass of your string. Okay? Then it has the imaginary parts, which are on this evenly spaced ladder, which is self-conjugate. And it has deviations, which are, you expect, exponentially small in system size. Okay? Under certain conditions. Okay, so the string hypothesis that you make is to neglect all these exponentially small deviations. You can't do that for everything you calculate, but the first, the first thing you want to do is use the fact that these are exponentially small. Okay, so this is just a string. Now, strings are really bona fide particles. They have energy. So the energy of a string is just the summation of lambda squared within a string. Okay? So you can just sit down and write that and do the calculation. So the energy of a string of length J, so here alpha is a label for the string. A is an internal label for the rapidities within the string. And J is the length of the string. Okay?
Excuse me.
Yes?
Lambda alpha J is a real number.
Lambda J alpha is a real number. Okay? Even if it's a 2 string, it's a real number. Because the 2 string is characterized by a real center, which is lambda 2 alpha. And then the 2 rapidities are lambda 2 alpha plus IC over 2 and minus IC over 2. C bar. Right? So the energy of a string is like this. So you've got the lambda alpha J squared. But now there's another term here that comes from just summing this thing here. Okay? So you need to take the square and you sum it so it becomes proportional to J cubed. Okay, and the coefficient of proportionality is like this: c bar squared over 12, j times j squared minus 1. Okay, so and the momentum is just j times lambda j alpha. So this thing here is like a binding energy. Okay? So your particles act as delta potential wells for the other particles, but now the potential well goes below, so you can have bound states. But the more particles you put into the bound state, the more attractive the bound state, the potential becomes for the other particles. Okay? And because the delta function is not saturating, it can take arbitrary large values, there is no limit to the binding energy that you can have. If you throw more particles in, the binding energy grows faster and faster. It grows with the cube of the number of particles that you have. Therefore, from the very beginning, there is no thermodynamic limit possible for the ground state of the attractive Bose gas. The ground state of the attractive Bose gas is a state that's known as the Maguire state, because Maguire wrote it in the 60s to look at it, explicit expressions for the wave function, things like that. But if you want, people looked at that and they thought this is nonsense, this is not interesting. If you read also Lieb's paper, they make some comments about the bound states in the attractive case, because they're worried about completeness of everything, but they specifically state that because the attractive case does not have a proper thermodynamic limit, it is not interesting, point to the line. Okay? But actually it is interesting because you can realize it. So what you can do, of course, is consider, for example, well, two different things. So with Pasquale, actually, a few years ago, what we did is that we looked at the properties of these bound states. So if you have a line, so a large system, and you have a certain bound state of a certain number of particles, you can just do stuff with it. You can try to scatter atoms off it. You can try to break it up in pieces and see what happens. So you can compute correlations. And the nice thing is that because you see you have explicit solutions to your beta equations in this limit, you can actually do the calculation completely analytically. Okay? There's no numerics involved in here. You can just get explicit functions for all these responses. And the attractive gas can be constructed experimentally. Of course, they can't go to the ground state, but they can get to a situation where at least some bound states form, some isolated bound states form. Okay, so it would be nice in the future to do that. And Pasquale actually, since those years, has kept on working on this. Still today, there's a paper of his where he relates all of this to the KPZ, and then he still uses all these equations in there. So you'll recognize many of the things in these things. So this is still ongoing research, if you want. Now, I will actually, in view of time, skip over the derivation of the reduced set of beta equation for strings. Beta equations for strings, essentially, let me just repeat the philosophy behind it. The philosophy behind it is that these strings here are to be seen now as true bona fide particles. So you get a reduced description for the system in terms of the rapidities of the centers of the strings. In a sense, if you have the beta ansatz for n particles in the attractive regime, your beta equations are equations for n parameters, where n is the total number of atoms. If you're in the attractive regime and bound states form, and the system is large enough, you can reduce that to number of strings independent particles. Because if you have a 3 string here, I don't care about the positions of the 3 rapidities, you just tell me where the center is, and the other 2 positions, they fit this pattern here. So instead of 3 parameters, I just need 1. Okay, so you get a reduced set of beta equations for these particles, but now of course the way a 3 string, for example, scatters against a 1 string, it's complicated because there are the sums of the original phase shift, so you need to rewrite the beta equations to take that into account. You will find that done specifically in the notes with all details. Okay? And essentially the calculation here is absolutely identical to the calculation that you would do, for example, for the XXX spin chain. The calculation of the phase shifts in there is identical. So it's you've got these rational functions of rapidities. Just need to take some products, reorganize the products, take care of all these cancelling deviations, and you get the reduced set of beta equations. I presume Marton will do all of that. But you can maybe you won't, but anyway, in principle it will be done. Anyway, you can look at the notes that you still don't have, but you'll maybe get at lunch or something, where this is all done, and then you'll see what it is. You also have descriptions of excited states on this, but I mean, I think I'll just let you read the notes to see how that goes. Okay, so the main message is that, first of all, the change of sign of interaction has drastic effects on the physics of the system, namely the ground state collapses into this hugely bound, macroscopically bound state with an energy that kind of goes to something ridiculous, n cubed. And of course, the nice thing is that you get effectively new particles showing up. So instead of having just type 1 and type 2 modes, like in the repulsive case, you here have, all possible strings. So you suddenly have an infinite number of particles in there. There's just these strings for arbitrary lengths. Okay? So, I mean, we only have like a half hour left. So I was thinking that I could just show you maybe some ongoing things that are based on the Lieb-Liniger model. That, I guess unashamedly it's stuff that me and my group are doing. There are many other people in the world still working on Lieb-Liniger. But maybe, I mean, if you're interested, I can show you some of these things that we are currently working on with Lieb-Liniger, just so you get a bit of a taste of where it's all going and why it's worthwhile to still teach Lieb-Liniger. So, do you have questions before I start doing that? Or do you want me not to do that and to just answer questions? It's okay. You decide a little bit, because you got me for a half hour. So. You go for it? Okay. So let's just see. Jeez. Maybe I have to use the other. Hang on, let me try something.
If you go to the first one, we will.
Hang on, shoot.
No, it's 1,200.
You are on air.
Yeah, that's fine. Well, maybe that doesn't work then. Or should I use the other beamer? Or?
Can you go to the first one? The first resolution there.
1,200.
1,200. Okay, just select that one. Yes. Okay. It's fine. It's okay.
Confirm. You should.
Confirm.
8.
Do you see my mouse?
You didn't confirm.
Try again.
What about that?
There's my mouse. Okay.
Don't move your mouse.
Yes.
Perfect.
Yes. Okay, good, thank you. Okay. Okay, so I just want to illustrate extremely quickly a number of research directions that we're basing essentially on our capability of doing loads of stuff with Liebig-Liniger. So let's just go through that. I want to talk to you about properties of the repulsive gas, so essentially correlations, things that I haven't had the time to teach you. I'll give you a 5-minute crash course on the ideas related to the algebraic Bethe-Ansatz that make all of this possible, and then I'll talk about all these other themes here. Of course, if you're interested in these things we can talk about later. Okay, so the model we focus on is Liebig-Liniger, as we have seen, both for repulsive and attractive cases. So what we do essentially is relatively straightforward. We like to translate every physics question that we have in questions on beta eigenstates. So you've seen already how to construct the beta eigenstates for Liebig-Liniger. What we haven't talked very much about is how you manipulate such states and how you extract information from them. Okay, so what you would imagine in normal quantum mechanics is that you start from a given state, you apply a certain operator on it. This operator is a matrix in Hilbert space. Okay, it's represented by some numbers. These numbers, these matrix elements here for various operators, in general you can see they're quite difficult to calculate because each beta wave function here is a summation over n factorial terms, and doing this integration is just a bit inhuman. So calculating these things is a big challenge, and that's the subject essentially, or it's one of the main accomplishments of the algebraic Bethe-Ansatz, to make such calculations practically possible. Okay? So if I get invited to Firenze again in the future, then I will give you a course on the algebraic Bethe-Ansatz to show you how to do this. But let me just very quickly give you the idea of the algebraic Bethe-Ansatz. So the idea is that we're kind of constructing our integrable models straight from the air, if you want. So what's a useful definition of an integrable model? Well, an integrable model is a model that has many conserved charges that you can display. So there are sets of integrals of motion, i's here, that are non-trivial quantum operators that all commute with each other. They're all simultaneously diagonalizable. Now, if you're a mathematician, what you try to do is to classify things. So you say, okay, let's just build a framework to construct integrable models. And how do we do that? Then we might say, well, okay, what we're going to do is, instead of constructing these operators specifically, what I will do is define a kind of generating function for these operators. So let me define a function which is a transfer matrix, just a terminology, whose essentially power series in this auxiliary parameter lambda whose coefficients in that series are the conserved charges. Okay, and then the statement that all these charges commute with each other becomes equivalent to the statement that the transfer matrix at different values of these rapidities commutes. Okay? So now what we're looking at is a single object with taking values in Hilbert space, but living essentially with an argument in the complex plane. And if this object has this property here, then we have constructed an infinite family of integrable models, because we have an infinite set of conserved charges, any of which, or any combination of which, can function as an integrable model. So now the challenge becomes to find representations of this equation here. Okay, so the idea is that there's one nice thing about matrices, okay, is that when you take traces of matrices, the order of the matrices in the trace doesn't matter. The trace remains invariant. So let's just lift this equation here one step up by introducing some pseudo space. Okay, it comes out of nowhere. It's called the auxiliary space. And we say actually that the transfer matrix here is the trace in this auxiliary space of another operator, another object, which is called the monodromy matrix. So the monodromy matrix is now an object living in Hilbert space tensored with auxiliary space. Okay? And now the statement that the transfer matrices commute becomes equivalent to the statement that this identity is fulfilled. So the trace in the, if you take a tensor product of two of these auxiliary spaces, you define these objects here. So this is now an equation in Hilbert tensor, auxiliary tensor auxiliary. Then this equation here is equivalent to the statement that the trace of this commutator vanishes in this space. So if you trace out all these two auxiliary spaces, this thing should commute. Okay? So, well, what, so you want this, this trace to be 0. So essentially, you have the commutator here, T1, T2. So trace T1, T2 has to be equal to trace T2, T1. Okay? Now, what is the most, generic solution you would like, or you would have here? It's that T1, T2 is related to T2, T1 by some transformation, some invertible map. Okay? So what you have is essentially such a relationship here. So there's an intertwining relationship relating T1, T2 to T2, T1. Okay? And R, the R matrix here, is the matrix that performs this intertwining. Okay? So if you find essentially a realization of this equation here, you found yourself an infinite family of integrable models. Okay? So now you see it's a fun classification game, because just looking at this equation here, you can write, first of all, a compatibility condition for this algebra here. So if you take a product of 3 auxiliary spaces and define T1, T2, T3, and reorder them, you can do that in 2 different ways. And in order for the algebra to be consistent, the R matrices here have to fulfill a certain relationship, which is the Yang-Baxter relation. Okay, so the Yang-Baxter relation is simply the compatibility condition for the algebra of monodromy matrices. Okay? And you see, we haven't specified anything yet. Okay? We haven't even specified the Hilbert space. Doesn't matter. We haven't specified the auxiliary space. Doesn't matter. If we find matrices here, so the R matrix, you see it intertwines 2 of these things. The R matrix lives in the tensor product of 2 auxiliary spaces. Okay? So of course, if these spaces are just U1, it's simple, just phases. So then Yang-Baxter is obeyed. But then you want to glorify this to something more complicated. So you say, okay, I will look at an auxiliary space that is 2-dimensional. Okay? So then this becomes, you see, if your auxiliary space is 2-dimensional, then R, living in the tensor product of these 2 spaces, is a 4x4 matrix. So then you go out looking for solutions to this equation in terms of 4x4 matrices. Okay, and then you find simple realizations. And if you're Rodney Baxter on a boat between India and England in the good old days where you could lock yourself in a library for 2 weeks and not be bothered by anything, email and things like that, then you find more complicated realizations of this relationship here. Okay? So, but that's the way it goes. So as a mathematician, what you would do is you would define a space, your auxiliary space, and you will look for solutions to this compatibility condition in these spaces. Okay? This is a job which has not been performed. We do not know a classification of these matrices for arbitrary spaces. It is not known. There are very complicated constructions that allow you to generate solutions to this. So this is essentially the origin of the concept of quantum groups. Quantum groups were used to essentially lift classical R matrices to quantum R matrices with specified algebraic structures. But in general, this is still open how to do that. Okay, but anyway, so that's another thing. Now, when I teach algebraic data ansatz, it's quite nice because what I do is that I start from these considerations like this, and at each step, mathematically, I make the simplest choice that you can possibly make. You want a non-trivial matrix, okay? So you want something that looks very much like the diagonal. Okay, so you say, all right, so what's the easiest deformation from the diagonal? Well, we put one off-diagonal element there, and then with symmetry we have that. And then, while we don't like complicated functions, if they're just constants here, that would mean that essentially we have operators in there that commute with constants. It's not interesting. We want to embed the functional dependence. What's the simplest thing which is not a constant? Well, it's a function with a single pole. Okay? You put that in there, and then you look and you see that you can find a solution to this. Okay? So, for example, this rational R matrix is the simplest solution that you can find for this, these relationships. And then essentially what you get in the end is that you derive the XXX Hamiltonian from making the simplest non-trivial mathematical choice at every step. Okay? And the Bose gas is very, very similar. So the idea is that these monodromy matrices, you can write representations for them where you now look for objects in a specific Hilbert space. So you say, okay, let's just take, say, n sites, and on each site we have a local Hilbert space, and then we construct matrices that will live in this Hilbert space. Then you can construct XXX, you can construct Liebniger, and what happens is that you get an explicit form of the monodromy matrix in terms of products of so-called L operators. And then, of course, because you've got the monodromy matrix, you can take the trace. When you take the trace, you get the transfer matrix, and then you can compute your conserved charges. So that's the way you would derive, for example, the XXX Hamiltonian. You make all these simple choices, you choose the simplest representation for the L operator that fits. Essentially, this is just the R matrix evaluated at a certain point. And then you look at the first conserved quantity, the transfer matrix, essentially, so that's just momentum. And then the first non-trivial one, just taking a derivative, you derive the XXX Hamiltonian. Okay, so it's an extremely beautiful way of thinking about integrable models, because you start from the algebraic structures that are inherent to all integrable models. Okay, so that's all very nice, but it all does stuff that we could do before, right? Write down the XXX chain and the Liebniger model and solve them. But there are other things that it can do. Okay, so well, let's see. The nice thing is that wave functions within the algebraic Bethe-Ansatz are extremely simple objects. So the monodromy matrix here you can write as a matrix in auxiliary space, in this case a 2 by 2 space, where each of these objects here is now an operator in Hilbert space, in the full Hilbert space. And the interpretation is that, it's like a spin algebra if you want, B will be a raising operator. Okay? So B is some incredibly non-local, really nasty looking kind of thing, but which you never need to explicitly write down, but which essentially creates for you eigenstates. So now our beta wave functions, which were these factorially large sums over these free waves, within algebraic Bethe-Ansatz, we write it as a product of these raising operators acting on some pseudo-vacuum, okay, some reference state, it's called. Now, in the case of the Bose gas, this state here is just, the state with no bosons, and this B operator is just a mess, okay? But it doesn't matter, because this is kind of cool. The B operators, they commute with each other, okay? And the statement is that if you were to project that ket state onto real space coordinates, you would get the beta wave function, okay, for free. Now the whole problem is translated into an algebraic problem between these operators here. These operators obey an algebra that comes from the relationship, R12 T1 T2 is equal to T2 T1 R12. Okay, so that's why they're intertwined. So, RTT is TTR, it's a quadratic algebra. Okay, so the commutators of these operators here with each other, it's not like a Lie algebra, it's a quadratic algebra. The commutators becomes a bilinear of operators. Okay, but you can still do logic that. So all the questions that you have are translated into algebraic questions on these ABCD operators. You can do everything. Now, of course, the problem is that how do you relate these operators here to the physical operators that you're interested in? So in the case of the Bose gas, the psi dagger, another operator. In the case of spin chains, local spin checked. So for the case of the Bose gas, a partial solution to this was found in the late 80s by Nikita Slavnov. Okay? But I think the kind of complete solution to the problem for fundamental lattice models, and therefore all models that we know, was found by the group of Jean-Michel Maillet. Okay, so for example, for the case of spin chains, it's quite nice because you've got simple spin operators here, right? So SU2. And then you get this mess of operators obeying quadratic algebras, okay? And then the fact is that it's easier to do computations with the right-hand side than with the left-hand side, okay? Because on the right-hand side, these operators have almost magical properties. So there's a way then to translate the matrix element, for example, of these local operators here in the basis of beta states becomes essentially reference state, whole big bunch of products of A, B, C, D operators, and then reference state. And these things can be calculated because the algebra of the operators is known. Okay? So this is a very beautiful theorem. It's due to Nikita Slavnov, published in 1989. It's possibly the most useful equation that came out of the algebraic beta ansatz, because it kind of changed the beauty of the algebraic beta ansatz into the solution to all engineering level problems in integral models. Okay? So the key is that the Slavnov formula allows you to compute the overlap between two states. One state has to be a solution to the beta equations. The other state is arbitrary, but is created by the operators in the quadratic algebra associated to the model. Okay, and this overlap here is given in a very beautiful form of a determinant of a matrix, which is related to, again, just a derivative of your transfer matrix. Okay, it's extremely beautiful. It's the same thing for all simple models that have just one-step beta ansatz. It's the same formula. Okay, so a couple of comments. Imagine calculating a matrix element for a physical operator using the real space representation of the wave functions. So say we do it with the Bose gas. We start with the vacuum, where we have one wave function, sum over permutations from 1 up to n factorial of these beta wave functions that we had, these psi n's times creation operator and then creation operator, creation operator. And then we say, all right, let's do like a density operator, psi diopside here in the middle. And then we have the other state here. So we want to calculate this. We get an n-fold integral of a product of two n factorially large sums. Okay, so it's a mess. You can't do it. So the kind of computational cost of this is extremely high. But here you have a determinant. So if you have one beta state characterized with rapidities mu, one beta state characterized with rapidities lambda, then you calculate your matrix element, you reduce it to a determinant. A determinant computationally is calculated with order n cubed steps. Okay? So it's a substantial reduction. That really makes calculations possible. Okay, so it makes also other things possible within the algebraic beta ansatz. You can prove the Godin formula for the norm of states. So essentially, everything is normed. You have now access to normed states, and also these matrix elements of operators. So that's one of the big things that we've exploited in the past, to explicitly calculate things. All right, so let's just see what this buys you. So what you can do is many different models calculate some, correlation functions or things like that. So let me just show you a couple of things about the repulsive and the attractive gas, and then some. So I'll be extremely quick here. Okay, so that's a paper from 2006 with Pasquale. So the idea is that you calculate then density correlation functions in the Bose gas. So you construct the ground state and you measure the space-time dependent density correlation function. Now this correlation function you can write in a Layman representation. It becomes a summation over intermediate states of an operator acting on the ground state, going to the intermediate state, and then giving a contribution at a specific momentum and energy. Okay, so here's momentum. Yes. Momentum is on the horizontal axis, energy is on the vertical axis. Okay, so we've talked about type 1 and type 2 modes. It should wake up again. I don't know. So,
There is one.
there's one just here. So we've talked about type 1 and type 2 modes, right? Now, for example, here you see there's this line that follows here. That is the type 1 dispersion relation. Okay, so it's linear in k at small k. So it's linear in k at small k. And then it becomes quadratic in k at larger k. The type 2 dispersion relation, you see better on this one. So this, by the way, is for low interaction, for high interaction. The type 2 relation is the one at the bottom here. Okay, so why does it curve back down? Well, that's simply because if you have a hole, you have the Fermi C, and the hole, if it goes from, if it's at the boundary, it's got 0 energy, but if it goes all the way across, it also gets 0 energy again. Okay, so that's the 2kF excitation that you have in here. So, for example, if you do this, right, you look at the excitations. So these are your type 1 excitations. These are your type 2, and your uncap mode is the one sitting there. Okay, but that's a way to compute the correlations. So you just you have this movie where you crank up the interaction starting from c is equal to 0, and then you see the stiffness of the system appearing in there, changing the dispersion much more into a little bit above that dispersion. Okay, so that's what we did. So these calculations are for, at that time, 150 particles. In the meantime, we can do many more. Recently, with an ex-PhD student, Miłosz Panfil, who's now in Italy, actually, we extended this to finite temperatures. So here, essentially, what we do is that we calculate, again, the density-density correlation function, but on a thermally excited state. Okay, so you just get some effects on that. So that's one thing that we did recently, and we're currently fitting this with experiments, essentially, that are performed here in Florence. So just a couple of words about the attractive model. We've talked about strings, okay, beta equations. These are string solutions. So what does that give you? Essentially, so all these things were looked at in the past, these states here. But with Pasquale, again, we looked at the correlations of this. So these are strings, the particles. We talked about that. And now what you can do is, because you have explicit solutions to the beta equations, you can just replace those explicit solutions in the determinant forms you have for matrix elements, etc., and just compute everything about the physics of this. And now there's something very interesting that occurs here, because you might know about the Mössbauer effect. Right? So if you have a crystal and you essentially scatter light on it, you can essentially get energyless scattering, where all the crystal, the incoming thing scatters against the whole crystal. There's no energy dissipation. So here, in the repulsive case, say you were scattering a photon on your atoms, then you would scatter off one atom, and this one would have a bit of rigidity, and essentially it wouldn't work like a crystal. But in the attractive case, it's a bit like in a crystal, because if you scatter one photon, essentially you can get, again, energyless scattering in there. So it should be very efficient experimentally to do Bragg spectroscopy on this, because you would just see a massive peak, essentially, at 0 energy. Okay, but these are just experimental predictions that we put out, and they haven't been seen yet, but maybe one day, so we'll see. Okay, so that's for the attractive case, just our applications. Now, one of the areas which we're trying to develop now also is to use integrable models as a smart basis for renormalization. Why do we want to do that? Because we're always assailed by the question, oh, why do you do integrable models? Nothing's integrable in nature, you always have junk, so you should just learn how to treat junk. Okay, so this is a way to treat junk, just starting from the integrable model. You say, okay, so we're always bothered again by people who tell us, you don't have a trap in your calculations. Yes, there is no physics in the trap, as many famous people have said, and as from now on we will repeat incessantly. It's not where the interesting physics is, but it would be nice to be able to treat it. If you put a trap in the Lieb-Liniger model, you break integrability, therefore you can't do anything with your beta wave functions. But actually, maybe the trap is a subleading effect. Maybe the interactions between the particles are much more important than the trap. So what you would like to do is start with the eigenfunctions of the interacting system, and describe the effects of the trap in some form of perturbation theory in that language. So you're used to doing perturbation theory, renormalization with free particles. You know, you just put epsilon of k is minus 2t cos k, and then you construct your things. So here the idea is that you do the same, but with the beta wave functions as basis. Okay? So you have your integrable Hamiltonian, your perturbation, and what you're going to do is rewrite this perturbation in the basis of the exact wave functions of your integrable theory, and then see how you do. Okay, so then you follow essentially the idea of Kenneth Wilson, allow him to solve the Kondo effect, and then you just try to do some numerical renormalization in the basis of beta eigenstates. So this is a long-term collaboration with Robert Koenig. We've been working on this for many years because it's extremely difficult to implement, but anyway, we're kind of making progress. So that's one case that we published a short while ago, where you just have a harmonic trap on your gas, and you see the effects of the harmonic trap. So of course the harmonic trap will take your uniform gas and will concentrate its density mostly at some point in space. So these are just density profiles computed using this numerical renormalization group based on integrable models. Yeah, so that's one thing. I'll come back to that. If you allow me just a few more minutes, I'll just very quickly do things. So out of equilibrium is one thing where I'm really trying to spend a lot of time and energy on this. One of the reasons is that out of equilibrium physics is extremely interesting. So even if you have classical simple systems that are driven, you get sometimes very nice little behavior. So one nice illustration is the Kapitsa pendulum. You take a rigid pendulum and you just start vibrating it very quickly. And then what you see is that the equilibrium point just shifts to the upper position. So my son has Lego, or I let my son play with my Lego. But you can construct such a Kapitsa pendulum out of Lego. So here it oscillates up and down at about 20 Hertz, and it's enough to just invert the equilibrium. Okay, so that's where I want to go long term. What I want to do long term is take an integrable model and just keep on shaking it and see what happens. But we can't do that yet. We can do simpler things though. We can do like quenches. So there are many experiments in there that are very interesting. Possibly the single most motivational experiment there is David Weiss's experiment about the quantum Newton cradle. So this is quite simple. You start with the gas at the bottom of a shallow harmonic trap in 1D. Then you perform so-called Bragg pulse. You essentially just shine light very hard on your system, and you populate momentum modes around plus k and minus k by a microscopic number of particles. So then your gas physically separates, climbs the potential wall, slows down, and then reverts and comes back towards the middle. And then here, they collide. So if you're in higher dimensions, the thing that you expect is that the gas is just going to go boom, boom, boom. Right? It's going to re-equilibrate, it's going to reform a state like the ground state. But what happens here is that because of the constraint dynamics, because of the vicinity to the integrable point, the gas keeps doing this. And it does this for hundreds of oscillations. Okay? So these are density profiles taken as a function of time. In those days you could do 50 cycles, now you can easily do many hundreds. So that opens up many questions actually. So how do you really understand the lack of thermalization in the system, how it's related to ergodicity, what's left of that in 1D, what does integrability have to say about that? These are really big issues of research now, so many people are arguing about these things. Okay, so that's one motivation. So in terms of out of equilibrium things, there are a number of things that we've been doing in Amsterdam. So with Robert, fire alarm. So with Robert, we treated trap lead linear, and let me just very briefly mention some really completely fresh things. I'll do that at lightning speed. Quantum quenches. What's a quench? You prepare a certain state, some state of a certain Hamiltonian, then you change the Hamiltonian. So it's very non-trivial what happens in there. What you want to calculate are just time-dependent observables after you do that, to see how the system re-equilibrates if it re-equilibrates. Okay, so then you open up questions also about generalized Gibbs ensembles. Maybe some of you are working on that, because I guess some of you are students of us and the earlier things. Okay, so the idea here is that you can recover the long-time dynamics from a generalized Gibbs ensemble here. So people are arguing whether this is correct, whether this is efficient, things like that. That's the idea. Okay, so the implementation of this, let me actually skip this. If you're interested in GGE, let's just talk about it. So let me just give you some examples. You take Bose gas and you turn the trap off. That's a form of mild quench. So what happens? Well, of course, it's a bit difficult to do that. Let me just show you some movies. So these are two different movies. The one on the left is releasing a gas with a high interaction, so the Fermi velocity is much higher, so the thing re-equilibrates much faster. And then if the interactions are milder, then the sloshing back and forth is much slower. Okay, so this is the kind of out of equilibrium, time-dependent stuff you can do with numerical renormalization. Let me skip this. You can look at momentum distribution functions and things. You can compare predictions of GGE. Again, maybe this is. So another example, we talked about the attractive case. There's an interesting realization that's known as the Tonks-Giraldo, the super Tonks-Giraldo gas. The idea here is that you start from the ground state of the largely repulsive gas, and then at t is equal to 0, you switch to attractive interactions. Okay? But this switching is sudden. You can't form macroscopic bound states. So essentially you remain with the gas-like state. But it's just that from that point onwards, you can form bound states if you so wish. Okay, so you see signs of bound states appearing in correlation functions. So the nice thing is that the correlation functions start looking different. You remember that ones for the repulsive case had a very large response in the Bogoliubov branch. Now you have much higher responses in the lower energy hole-like sector. Then you open up new things here. Okay, so this is again work that I did with two of my PhDs, so Miłosz and Jakob Odenardis. Capital D should be there, I should change that. We're still in Amsterdam. So again, we're trying to see if experimentalists can see stuff like that. So, you know, there are some interesting features about these correlations that again I could skip. Okay, then some other examples. This one is motivated by the David Weiss experiment. So you remember these colliding gases like this. So if you look at the gases as they are colliding, really what you have is a counter-propagating fluid, you know, going through a fluid. So one of the models that we have for that is that, okay, we say, all right, let's just prepare the vinegar in a state where half of the gas is moving one way and half of the gas is moving the other way, and let's see what that tells us. Okay, so it's just like a kind of complete caricature of the experiment. But this is quite nice because what you do is that you take your Fermi seed, you split it, and then the selling point of this is that we like Charlton Heston, so we call it the Moses state because you split the seeds and then you see features of these things here in the correlations. So now you get a dispersion spectrum, which is a generalization of the lead type 1 and type 2 modes. So Tessa here did all these beautiful plots here for specific cases. So you see generalizations of type 1, type 2. You get many more branches appearing in the correlations. And then you can compute these correlations also with these methods that we have of summing up matrix elements. So then you get very strange looking correlations that are presumably eventually, you know, maybe not observable explicitly. And then the momentum distribution function would be the thing that we would like to fit eventually with Newton-Cradle-like experiments. Okay, and then in the last minute, if you allow me, let me just mention the very latest, you know, fresh out of the box result that we got. This is about an interesting quench problem where you start from non-interacting bosons in 1D, and then at t is equal to 0, you switch on repulsive interactions. Okay, so what happens is that you start from a momentum distribution function which is a delta peak at k is equal to 0, and then because there are large fluctuations, if you want, in the location of the particles in c is equal to 0, when you turn on the interactions, it could be that particles are close to each other and then start repelling, so then they kind of blow away from each other, and the momentum distribution function will start looking very different. Okay, so this is a very difficult problem to treat because, yeah, so you know, it's a long story actually. You can't implement GGE. The charges are quite bad. You can get partial solutions using kind of lattice-ified model here. So this is work with Marton, Aditya Sharchi, Yanji Cha. One of the things that we did recently is that we used a new approach for quenches to do this. So since you've seen thermodynamic beta ansatz, a Yang-Yang formalism, I can explain that to you very, very briefly. The idea is that you consider the initial state in the Hilbert space of the pre-quench or the post-quench Hamiltonian. The post-quench Hilbert space, so this is the same quantum state, just expressed here as a linear combination of eigenstates in this Hilbert space here. So there's a distribution of weight all over the place. Now the point is that this defines for you a kind of pseudo-action functional. Think of a, it's a bit like the Gibbs free energy that you write when you do Yang-Yang, except that now it's not the energetics that send it, it's the overlaps. But then you can do the TBA like we did in order to find the important states that give you the long-term and the relaxation processes. Okay, so the message is that essentially you can solve this quench problem exactly with these methods. Let me actually not mention all these things. Let me just show you the answer. So the result is predicated on the existence of exact overlap formulas between initial states and beta eigenstates. So this is something that my group found for the case of the VEC to the vinegar quench. And then you put that in this generalized beta ansatz, thermodynamic beta ansatz product, and then you get the root density distributions of the state representing the steady state. Okay, and this is an exact thermodynamic calculation, so you've really completely managed to solve the problem. So you see that it's non-thermal as well. So this is ongoing work with Lieb-Liniger, at the very second. It's published, well, it's not published yet, but it's been on the archive for a while, and where we're trying to extend these things to other situations and other models. So I think there's a good future to be had in this direction. So yeah, I mean, what I would like to leave you with is maybe just this message. So these integral models, although they're a bit artificial, they form an extremely good basis to investigate extremely complicated questions that really you can't investigate with other methods or with other models because you don't have the right tools to do it. There's of course loads of numerics that you can do, but I think integrability really has a lot to deliver in either equilibrium properties at more difficult regimes, say higher energy, maybe with temperature and things, or in the context of out of equilibrium physics, where, quite frankly, alternative methods are very hard to come by, and whether they are trustworthy or not is very much the question. So at least we can build up a catalog of cases that we can understand in excruciating detail with these things, and hopefully that's at least a service to the community. So anyway, thank you for your attention, and if you have questions and things, I'll be happy to answer them. I'm here today, and otherwise on email. So thank you for your attention.